My esteemed listeners, in this tutorial, we will continue with our transform and conquer algorithm design strategy. Of course, the third version of transform and conquer algorithm design strategy, namely the problem reduction. As the name itself would imply, the problem reduction version converts or totally transforms the original problem to be solved into a problem of another type where some readily algorithm is available. Therefore, it is a reduction of one kind of problem into another kind of problem. Okay, the reduced problem will definitely find several algorithms. Therefore, we will draw one of the apt algorithms from the cupboard and we will solve this, and that is altogether getting the solution from the original problem. I repeat, the original problem is reduced to problem of some other kind for which different algorithms are available. Say algorithm A is available, to be specific. Using this algorithm A, we totally solve this reduced problem and solution to problem 2 is obtained. This altogether means obtaining solution for the first problem kind, that is original problem kind. We will discuss several examples over here, at least 5 to 6 examples, which befit the reduction. Okay, the very first problem is finding least common multiple, that is LCM. Our middle school procedure tells that, and if you consider 25 and 35, our middle school procedure, our nostalgia will just remind us how we used to find out the least common multiple. We used to find out prime factors of 35, 5 into 5 and 7, prime factors of 25, it is 5 into 5, and we would have selected the common multiples, common prime factors among the two prime series. So 5 and 5, one 5 is considered, and all the remaining other non-paired prime factors. So here there is no pair for this 5 and there is no pair for this 7, and we multiply everything, one common pair, one among the common pair, or several factors among the common pairs, if at all there are several common pairs, and the remaining pairless numbers, pairless prime numbers, and we multiply together. That's how we obtain. And we have discussed in our fundamentals of algorithms, tutorial 1 or 2, where tutorial 1 or it might be tutorial 2. Okay, you can revisit those tutorials to find how exactly we have found out GCD, greatest common factor, GCD, greatest common divisor for two numbers. This algorithm suffers from the fact that we need to develop a series of prime numbers up to the given number, and this suffers from a disadvantage of being inefficient because it demands pressing of some other algorithm into service. That algorithm is nothing other than generating a list of consecutive primes. Therefore this problem is converted into a GCD problem. Okay, and we have a excellent algorithm written by Euclid, a perfect algorithm to find out the GCD. We find the GCD using Euclid's algorithm, and then we will find out LCM by using the formula which goes something like this. Okay, LCM of two numbers, say M and N, here it is 35 and 25. Anyway, I will write a general formula. It is nothing but the multiplication of two numbers, okay, M into N, divided by GCD of M comma N. GCD of M and N. And we know GCD of M and N can be calculated by Euclid's formula, which can be simply stated as, I will write it here, GCD of M comma N equal to GCD of n comma m mod n, m mod n. Okay, this is nothing but the remainder. When remainder becomes 0, we will return m. We will return whatever that is in the place of m. Okay, therefore this problem, the problem of finding least common factor, least common multiple, is converted into a problem of finding GCD, and we used a simple division technique. We multiplied the numbers, integers, and we divided by GCD. That's how the solution is gotten. Reduction of optimization problems. Here is a problem. You can just go through, and let us say there is a situation wherein we need to minimize. Optimization problems will either end up in minimization or maximization. Let us presuppose such a situation wherein you know only the minimization algorithm, and the problem in hand is a maximization problem. By just utilizing this simple formula and by knowing only the minimization algorithm, we can obtain the maximization of the problem. That is maximization of f of x, the objective function involving decision variables x. Okay, the maximization of objective function f of x is nothing but minus minimization of minus f of x. Therefore, it is enough if I know minimization algorithm or minimization procedure in order to convert that problem into maximization problem. So problem in hand, the original problem was maximization problem. It was reduced to minimization problem. In the same token, minimization problem can be reduced to maximization problem by wedding minus sign with both the entire function, entire unit of the function, as well as the function itself. Okay, that's how you can reduce a maximization problem into minimization problem, and vice versa. And linear programming is yet another example of this problem reduction. Linear programming surfaces in operation research. It's an optimization of a linear objective function, and let us say how exactly problems will surface. Problems will be mostly surfacing in textual matter as a textual problem. Okay, in running sentences, a paint company produces both interior and exterior paints from two raw materials, RM1 and RM2. Okay, we never deeply delve into this, how exactly linear programming is solved, linear programming methods are attacked are solved, because it has been we have gone through this in probably in operation research. Therefore, it's a recall to memory. Following data about the cost and profits are available: tons of raw materials per tons of exterior paint and interior paint. Maximum daily availability in tons. It should be available 24 tons of raw material should be available for exterior paint in order to manufacture 6 tons of exterior paint and 4 tons of interior paint. For material 1 and material 2 demand is exterior. In order to manufacture exterior paint, it should be 1 ton, it should be 2 ton, and maximum daily availability of raw material of RM2 should be 6. And profit per ton in lakhs is for exterior paint is 5 and interior paint is 4. The question is, the daily demand for interior paint cannot exceed that from exterior paint by more than 1 ton. For exterior paint for 2 tons. Find the optimum mix of interior and exterior paints to maximize daily profit. Let us not go deeply into this particular problem, but anyway, it's very important to emphasize that this problem arrived in textual in running sentences as a textual matter, and this can be converted into an equation. This is called as an objective equation. 5 times x1 and 4 times x2. Here it is profit per ton, 5 times x1 and 4 times x2, and we need to find out the optimum mix of interior and exterior paints. Okay, the quantum of exterior paints is x1 and the quantum of interior paint should be x2, and this is given by the conditions, and these are all the constraints. 6 times x1 should be x1, and 4 times x2 should be lesser than or equal to 24. x1 plus 2x2 is lesser than or equal to 6. These are all the conditions laid out in the problem. Therefore, the problem, the mundane problem or real world problem, which is an optimization problem or linear optimization problem, came to us originally in the form of running sentences. We framed this into an equation. This is the main equation called objective equation. Then we framed the constraints in the form of equations once again. Then they can be amalgamated into the basic equation by removing this non-equality constraints by slack variables and other variables. Therefore, we end up in solving simultaneous equations. Problem came in the form of running sentences, a real world problem. It was converted into system of equations, and this system of equations can be solved by using what is called a simplex method, which was found out by US mathematician George Dantzig in 1940, way back in 1940. And this particular method has an exponential complexity. Okay, and there is a total reduction. Okay, the optimization, linear optimization problem, which came in the running sentences, like a person who is explaining his problem. Okay, which was just made as a textual matter. It was converted into an equation, set of equation. Okay, the conditions became constraints, and it ended up in system of equations. The problem never came in the form of an equation, that we should remember. And these system of equations were solved into simplex method. And solving this kind of equations, the algorithm available is simplex method. Therefore, we reduced the problem, linear optimization problem, into set of equations. This is a total transformation. Another important problem that can be solved by third version of transform and conquer is reductions to graph problem. Some of the puzzles can be transformed into graphs. This is a famous problem called Peasant, Peasant, goat, peasant, goat, wolf and cabbage problem. Wolf and cabbage problem. This problem is typically called, or traditionally called, this way. Okay. The problem is these four items, or four peasant, wolf, goat and cabbage, happen to cross a river. There exists only one boat, and in a boat maximum of two persons can be moved in this boat to the other shore. And if goat and cabbage were allowed to remain in one bank of the river, goat would naturally eat away the cabbage. On the other hand, if the peasant happens to leave wolf and goat over here in the other part of the other bank of the river, it is natural that wolf would eat the sheep. Therefore, wolf will eat the goat. Therefore, the problem is how exactly the peasant will see that all the three companies will be transferred to the other bank of the river. So it can be neatly converted into a graph problem. Okay, into a graph problem. Okay, it's something like this. So we will assume we will have some conventions now. Okay, we will have some conventions. The convention is we will write the river by a single line. Okay, single line, and this is one side of the bank, this is other side of the bank. Okay, if river is flowing like this, of course you should remember that the banks, right bank or left bank of a river, is identified by the flow direction of water. Let us say if the flow is flowing like this, if the flow is flowing like this, this will become right bank and this will become left bank. Anyway, that is immaterial. But anyway, as a matter of fact, okay, for the sake of information, just I am telling. So in the initial stage, okay, this is the left bank. Peasant will be here, wolf will be here, goat will be here, and cabbage will be here. There will be nobody on the other part. Okay, this forms the vertex. The state of the problem forms the vertex. Before it goes to the other state, there is a transformation. Okay, the peasant and goat will move in the first succession. Peasant and goat will move. So on this end now, here the state of the problem is, here there will be W, that is wolf and C on the left bank, who would remain, wolf and cabbage. On the other hand, on the other bank, right bank, P and G will be remaining. Boat has come to this end. Therefore, the boat is to be transferred. Boat is to be taken that side in order to bring the other people. Now, peasant will move. When peasant comes over here, who remains on the other part, other bank is peasant, wolf, cabbage. Peasant, wolf, cabbage. And goat will remain on the other bank because peasant has come back. Now, again, peasant and wolf will move to the other shore. And who remains here is the cabbage, and on the other shore, peasant will go and join. Okay, peasant and wolf will go and join the goat. Goat was there before. Now, in this direction now, P and G will move. That is, peasant and goat will move in this direction, and the state of the problem will be like this. On the other end, other shore, only wolf will remain, and here we will have peasant, goat and cabbage. Now, peasant will carry cabbage along with him because he knows at the other end only wolf is remaining. Wolf cannot eat the cabbage. Okay, therefore here what remains in this particular state is peasant, goat, peasant and cabbage. This should be cabbage, sorry. Okay, peasant, cabbage and wolf. Now, once again, peasant will come back, and in this shore we will find peasant, goat. On that shore we will find wolf and cabbage. Now, peasant and goat will move to the other side. They were the only two people remaining after so many crisscrossings. And here on the left end, when peasant and goat reaches this particular point, okay, all the items and all the parties are on the other shore. So this took 1, 2, 3, 4, 5, 6, 7 edges. 1, 2, 3, 4, 5, 6, 7, 8. 8 states. I repeat, it included 8 states and 7 edges. And this puzzle, which we told in running sentences, is converted into some kind of a graph. Therefore, and in order to draw a graph, we need the space. Okay, and over this Cartesian space, we represented a graph. Okay, where vertices formed the states of the problem, while the edges who moved from the other side to other side. Okay, from one end to the other end. Therefore, this diagram is called state space diagram, state space graph. There is yet another problem, very interesting problem. This problem is coming to be called as jealous husbands. there are n number of couples, n greater than or equal to 2 married couples who need to cross a river. They have a boat that can hold no more than 2 people at a time. To complicate the matters, all the husbands are jealous and will not agree on any crossing procedure that would put a wife on the same bank of the river with another woman's husband without the wife's husband being there too, even if there are other people on the same bank. Can they cross the river under such constraints? And we can solve the problem for n equal to 2, that is 2 pairs and 3 pairs. Okay, we will attempt. There are many ways of solving this. Once again, we take the recourse to a graph. Okay, therefore it is a problem reduction. Okay, puzzle is reduced to a graph. Therefore, this is a total problem reduction. When n equal to 2, there are 2 pairs. This is one part of the river or one bank of the river. This is the other bank. And if the flow is like going like this, once again I repeat, this will become the left bank and that will become the right bank. Okay, now to start with, both the H1, H2, husband 1, husband 2 and their corresponding wives, their counterparts will be here. First H1 and W1 will move. Here also there is a boat. In that boat only 2 people can traverse, okay, from one end to the other end. Okay, H1 W1 will go. Here remains on the other part H2 and W2. H1 and W1 will reach this shore. Once again H1 will come back, leaving behind his wife, and in this part there will be H2, W2 and H1, and once again H1 and H2 will move. Okay, here W2 would only remain. H1 and H2, W1 will be joining that particular shore, the other shore, right shore, and W1 will leave from here, will leave from there. W1 will come and join W2, and there H1 and H2 will remain. Now W1 and W2 will take a movement, and here, and all of them will be crossed. All of them will have crossed the river. Okay, when W1 and W2 makes the final journey. In nowhere we just crossed the conditions. We just complied with the conditions of the problem, and we could solve this. And there are many ways of making the pairs to move this side and that side. Okay, therefore this is one of the tricks or one of the solution procedures. Okay, this constitutes state space graph. N equal to 3. There are 3 pairs, H1 W1, H2 W2, H3 W3. In the first succession, W2 and W3 will move, and they will go to the other. This is the shore, this is the river. This vertical line shows the river. H1, H2, H3 W1 will remain the left shore, and to the right shore W2, W3 will reach. W2 will traverse back because there should be somebody to navigate the boat, and W2 will come over here, and she will join H1, H2, H3 and W1. Okay, then W3 will remain on the other part. Now W1 and W2 will leave, and here they become W1, W2, W3, and on the other shore H1, H2, H3 would remain. W3 will once again traverse, and she will come to this particular location, that is left shore. H1, H2, H3 and W3. On the other shore W1 and W2 are there. Now H1 and H2 will leave, and they will join H1, H2, W1 and W2, and other portion H3 and W3 are there. W2 will leave over here, and here becomes H3 W2 W2, H3 W3 W2. On the other shore H1, H2 and W1, and once again H3 W3 will leave, and they will become the pair over there, H3 W3, H1 W1 and H2. They were there before. Okay, on the other end only W2 will remain. I will continue with this once again in the next slide. Okay, H3 W3, H1 W1 and H2 on the right shore, and W2 alone on the left shore. Now H2 will leave and join W2. Okay, on the other shore H3 W3, H1 W1 would remain. Okay, a simple consideration will show as to how we can just do this and just exchange people, okay, and maintaining or complying with the condition of the problem. and now H2W2 will, both of them will leave and they will join the other party. Therefore here it remains vacant. Okay, this shore will be devoid of any people, and all the 6 will have reached the other shore. So it took 1 2 3 this is carried. Okay, 3 4 5 6 7 8 9 10 1 2 3 4 5 6 7 7 8 9. Okay, 10 states and 9 ages. Okay, so we saw in all the 5 problems, 5 kind of problems that we discussed, that there was a total transformation. That is, one kind of problem is converted into other problem. For example, LCM problem was converted into GCD problem, and linear programming problem, optimization problem is converted into system of equations, and the corresponding algorithm was drawn and pressed into service, the simplex method. And the maximization problem can be converted into minimization problem. It is a total reduction, and vice versa, minimization problem into maximization problem. Therefore, whenever we try to maximize or minimize, it is good enough if we know either maximization or minimization, because transformation is always possible. The fourth kind of problem reduction that we saw is the puzzle getting converted into a graph problem. Okay, and we saw 2 examples, jealous husband problem and peasant, goat, wolf and cabbage problem. So with this we conclude the transform and conquer strategy in 5 tutorial sessions. We completed everything, and the next session is next session on the annual is space time trade-off technique. Before I bring the discussion to the fore, bye.